a computer that uses quantum physics is going to do things in a different way than a computer that uses classical physics, non-quantum physics. And this already opens up a lot of philosophical questions, right? What can you actually do with a computer? What can you compute with the physics? If quantum computers are going to impact science before anything else, can we associate a monetary value to what quantum computers will allow us to learn about our universe? Almost like how much is the monetary value of, now I'm going to say something which is a little bit bigger, I don't know, relativity theory. So when it comes to talent, when it comes to education, I like to see people choosing, so the next generation of scientists and engineers to choose the right areas, to focus on the right areas. And there's lots of interesting things happening in quantum computing. And some of these areas are still completely completely new.
Welcome to another episode of the Quantum Economy Podcast. Today I'm joined by Simone Severini. He's now an engineer with Google, but when we spoke, he was still with AWS, where he started and led all Amazon initiatives within quantum, across the domains of product development, research, and infrastructure. He's not only a great thinker, but he's also a practitioner and was involved in some of the early startups in quantum computing, including Cambridge Quantum, now Continuum, and also Facecraft. He has advised governments and VCs on how to lay out strategies and how to invest in emerging technologies. In our conversation, we talk about how to build a fault-tolerant quantum computer, and we look at some insights on what Amazon is up to, the industry in general, where Simone think that things are heading, and we get philosophical and dance off into a very interesting conversation. So without further ado, here is the Quantum Economy Podcast with Simone Severini. Before we get into that, Amazon, AWS, Ocelot, the whole quantum computing space, I just wanted to take a step back to the philosophical applications of quantum physics. So for me, basically, I came to this with an intuition. I've been very curious about consciousness and how quantum physics moves into the real world in terms of applications. I was just, last time we spoke, I was just very curious about like your background as a philosopher now, like then into academia and now into the corporate world. Do you see this like building a quantum computer as something that like has an implication also on a philosophical level, how we perceive reality?
So it's a deep question. Now, of course, my background as philosopher, it's kind of a stretch because I studied philosophy in Florence as an undergrad student. So I can't say that my background is philosophy. I studied some philosophy uh, at the beginning of my academic career, let's say, um, meaning that my knowledge of philosophy is extremely limited, and I'm far from keeping up with what is happening out there in philosophy. So what I can attempt to answer your question anyhow, and there are obviously a number of intersections between philosophy of science and quantum computing, and even more broadly, aspects that have to do with ethics, aspects that have to do with moral philosophy, and so on. But let me focus for a second on quantum computers as an instrument for observation, so more epistemology. You see, we often think about quantum computers as machines that are going to allow us to save resources, specifically time, right, which is a physical resource, and it's fundamental in computation because the complexity of algorithms is often studied on the basis of the number of operations that are needed in order to solve a specific problem as the size of the input of that problem. So great, quantum computers offer theoretically some advantage for speeding up the solution of certain problems, which can have an impact in the real world because would allow us to solve certain problems that potentially cannot be solved today. But then what if we interpret quantum computers as instruments that allow us to create a novel interface with quantum physics itself? And here the opportunity has two sides. One is physics. You have a new device that creates a new way for learning about quantum physics itself. And indeed, as you know, the community expects that the very first applications of quantum computers will be in simulating quantum physics. Applications related to material science, for example, but even more fundamentally, certain aspects of quantum physics itself. So quantum computers as a instrument for experimentation. And second, quantum computers as machines that will generate data about the quantum physical world. And maybe this data can be reused outside of quantum computing itself. But, and I'm not sure if this goes at least in the direction of your question, what could be one of the philosophical aspects associated with quantum computers and my immediate answer would be interpreting quantum computers as objects for observation even before the term computer. Now, of course, the term computer is very broad and today is used in many different ways somehow. We have this idea that a computer is a machine that can do everything. What does everything mean? Some people even believes that the universe is a quantum computer, right? So that everything that has been created so far is the product of a quantum process. Is in fact the universe is in a quantum state and has been constructed through time via the evolution of the state, right? So computers as universal devices, meaning that can solve every computational problem that is plausibly solvable. But if you go back to the etymology of the term, calculus is a stone, right, in Latin. So there is a very strong connection with the physical world, right? So, so meaning quantum computers are, interestingly enough, natural objects that are governed by the laws of physics. And quantum computers can be seen almost as an excuse to bring us closer to this idea that indeed computers are objects that exist in the physical world. And because of that, they must satisfy certain laws associated with the physics that is behind their functioning. And indeed, quantum computers are, they bring us this idea in a deep way, right? Because a computer that uses quantum physics is going to do things in a different way than a computer that uses classical physics, non-quantum physics. And this already opens up a lot of philosophical questions, right? What can you actually do with a computer? What can you compute with the physics that is real? Of course, you can even come up with some imaginary physics. People can ask, what if you can time travel? So if you can time travel, then certain consequences are going to appear in computation. But maybe on the basis that this consequence seems to be very strong, maybe too strong, then there is a chance that you cannot time travel, right? So to me, to go back to your question of so about physics, specifically about quantum computation and philosophy, to me the great opportunity is in this interplay created between computation and physics.
Yeah.
And today there is a number of questions people start to ask about some fundamental physics questions that are seen through the lens of computation. Think about black holes. People discuss the nature of black holes and talk about entropy, talk about information theory.
Yep.
And this is due to the fact that somehow quantum information and computation have stimulated a conversation between computer scientists and uh, and physicists. And if you look at this conversation, it really goes back to the origins of quantum computing itself. I guess Yuri Manin, Richard Feynman, Rolf Landauer, Charlie Bennett, so the fathers, the pioneers in this space, they ended up to think about thermodynamics of computation, and ended up to think about automata, like certain type of finite state machines that generate, let me use the term physics, this is not exactly correct, but that generate uh, some worlds in the laboratory. And then questions of the type, once you raise information, what's going to happen from the physical point of view? Once you have reversible computation, meaning once you cannot delete, erase any information, what's going to happen, and so on. So somehow, even if you look at the very origins of quantum computers have not been taught primarily as an object to save time in computation, have been taught primarily as some devices that are exquisitely physical and use physics to perform computation with all the consequences that this brings, and all the opportunities and all the beautiful questions that they emerge once you start thinking about the interplay between physics and computer science, which is now vast and is pervasive. Because as I was just mentioning, it's beautiful and to some extent even strange that now there are people thinking about the natural black hole and use terms like entropy, right? Which of course has a dual nature. On one side, entropy can be seen uh, as a physics quantity, but on the other side, it has to do with information theory itself, right?
I mean, that I'm sorry for kicking it off in the morning with,
No.
with the philosophical journey, but yeah, I'm leaning towards a world um, being quantum mechanical at the foundational level. So, Feynman said if you're going to simulate the universe, it has to be done quantum physically, right? That's type of thinking. And I saw like you had that like philosophical background. I was like, my hinge was that you want to get people to understand how to apply quantum physics through quantum computation to real world problems, right? So that was kind of sort of where I was going. And
Yeah.
um, but I'm just before we get into the great work that you're doing with AWS and a little bit on the
So,
commercial
but
side.
Anders, I can tell you very quickly, my philosophical background is just an accident. So I just found myself studying philosophy, and while studying philosophy, I ended up to learn about quantum computing because my teacher, um, she mentioned that at the time, this was about 1996 1997, mentioned that there were interesting stuff happening in this space, and I got curious about quantum computing, but it's just random. I could have ended up to do something else entirely different. So in life, I
But
don't think we make a lot of decisions consciously.
yeah, no, okay, okay. Well, I don't want to dig into the consciousness and the quantum phenomena, but I mean, you keep coming back to some reference points that we had the previous conversation that we had, and I was just that curious on your take on um, kind of sort of the bridging of the classical world to the quantum physics and your view of the collapse of the wave function and where you're leaning in that fundamental understanding. And to me, that
Oh,
is, if you come at it as a scientist, and I've seen that a lot of like scientists has gone philosophical and vice versa. So I was just, curious on where you are in that essence of, um, if we build a quantum computer within a physical world, is there something beyond the computational pictures of physics that we don't
mhm,
get? Is it because that is kind of sort of where the philosophical dance comes in? If we lean towards it's all a part of computation, then from a materialist standpoint, it kind of sort of makes the story a little bit easier to go after. At least
mhm,
that's my view of it.
mhm. Yeah, so I mean, I'm far from being an expert of fundamental physics and the interpretations of quantum mechanics. I don't have a strong opinion on this. I don't think that I spent sufficient amount of time reflecting on what is the most plausible approach to describe the interplay between classical physics and quantum physics.
So
So
taking
sorry to disappoint you.
that's beautiful. You know, it's just a fascinating thing. We take it, we work with it, and we build actual things, right? But don't worry about like the underlying foundation. And it's always beautiful because I like that because there are so many things that we and your answers are to me like of a philosophical nature because you reason and reflect on that understanding. So, but we wanted to talk a little bit about like as I'm in the midst of rewriting my quantum economy.
Mhm.
I was just, you know, you had an academic background and you moved into a corporate environment. And I was just curious, like, on do you see breakthroughs in science now more coming out of these corporate labs in the corporate environment as in comparisons to the academia? Or do you think that we will still see a lot of breakthrough science done in academia? So, I mean, you are like a practitioner, you're both in the academia world and in the corporate world. And now my feeling was more money, more great minds like yourself coming in and working in a corporate environment. How do you see that evolving?
Sure. Myself, obviously, working as kind of administrator, I trust what scientists and experimental physicists are doing these days in building quantum
You always
computers. So my
downplay that. You always downplay that. You always put yourself in an administrator role. I've heard that
s-
before, but I don't buy
uh,
that though.
so my opinion is that innovation is happening across the board. There is good innovation happening in academia, and in fact, as a matter of fact, the people that are working and leading the largest industry projects in quantum computing, they come from academia. They were university professors historically, right? So somehow it's an analytic continuation of the work they were doing in academia, possibly without the need of writing grants with a frequency that they were used to in the past. Maybe a little bit more resources to focus on specific long-term bets. And I want to stress the importance of the long-term aspect. So, as you know, quantum computing requires a lot of different expertise, people that come from different backgrounds, require substantial investments for the long term. And we should set the right expectations, right? When people say, oh, quantum computers are, you mentioned the term quantum economy, right? And there's a number of realities out there where uh, governments, organizations are trying to push the narrative on quantum computing with the idea that this science and technology is going to create a number of jobs, for example, and really generate economic value. It's unclear what's timeline for this, right? And we should definitely keep in mind that the very first applications of quantum computers are going to be of scientific nature. Applications that have to do with our deeper understanding of quantum physics itself and areas directly associated with quantum physics. But I think that this is very important because science is one key step towards technology, towards innovation, and and we should keep open-minded about the fact that we will discover certain things with quantum computers that are very hard to predict. And I keep saying, and it's not my phrase here. I think I got it somewhere on the internet that quantum computing is simultaneously overhyped and undersold. This seems to be two things that are contradictory, right? But on one side, we talk about the marvelous things that quantum computers can do when it comes to solution of certain industrial problems. But then on the other side, we almost forget the fact that there will be areas where quantum computers could uh, create value, so primarily scientific, but also in ways that have to do with, again, with quantum physics itself. Think about quantum computers, for example, as logical coprocessors in quantum communication or metrology. So they will perform certain tasks which are fundamentally different than what we can actually do with classical, I mean, non-quantum devices. And there is a chance that the tasks quantum computers are best suited to solve are going to be very different from the task that we are currently proposing, and this will be discovered once there is the hardware, built it, they will come, right? So it's um, it's an important point here that quantum algorithms, for example, there's a number of algorithms out there that are heuristic algorithms. It's very difficult to determine the structure of these algorithms and the computational complexity. Is difficult to determine what they do on paper. And to figure it out, we need to have quantum computers. And when people ask, oh, what can you do with a quantum computer today? What are the important problems that you can solve with a quantum computer today? In my opinion, the best answer is, and again, I'm this is not my answer. This is John Preskill's answer, which I reuse. The most impactful application of quantum computers today is to learn how to build quantum computers of the future, which does not mean to demean the importance of quantum computers today. It's easy to interpret these as quantum computers are entirely useless, right? Because the only thing that can be useful for is dot 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 building other quantum computers, like a kind of self-referential activity. Well, I don't think so, because as we know, important applications of quantum computers that could impact customers, let me use this term, right? Could be simulation of simple physics models, are currently estimated to require hundreds of thousands of qubits, physical qubits. And the majority of applications maybe require in the order of 10 million or 100 million physical qubits. And so you see that the entire field is not there yet, but it will get there. And by the way, another aspect that people forget is the clock speed, right? Because people talk about, quantum computers are fast. Well, no. Quantum computers implement a richer class of algorithms, and these algorithms, for certain problems, use less operations. Specifically, for certain problems, an exponentially smaller number of operations, but doesn't mean that they're faster. In fact, if you think about microprocessors today, they're really, really fast, right? The quantum computers are going to have logical speed, meaning the time that it takes to apply gates, which is going to be probably in the order of the megahertz, right? Think about instead the gigahertz that microprocessors already achieve, right? And this could be at some point a bottleneck for application, which we should not underestimate. But anyhow, to go back to the question, what can quantum computers do today? Well, quantum computers are wonderful scientific experiments that allow us to learn more about how to scale, about how to build quantum error correction, and about the road that it will take us to certain regimes in which quantum computers will solve important problems. And by the way, these important problems will not have necessarily immediate commercial value. Could be problems that, as I was mentioning, may have some interesting impact in science that will allow us to see the physical world differently, and that will allow us to learn something about fundamental physics in ways that were unthinkable before the advent of quantum computers themselves.
Yeah, I mean, this is fascinating because you're at the same time sitting at a company that is customer use case driven. You start with the customer and you engineer back, and you have to solve or make. I always like the progress part of it, and I like the way of David Deutsch's thinking of creating better problems. I mean, I think Amazon is like customer driven, we need use cases, and at the same time you're saying, we're we're building a quantum computer to build a better quantum computer, but there are no use cases in sight. It seems kind of sort of contradictory to the philosophy of the organization that you were in. So I would be curious about, like, where do you see in the space of hybrid solutions, as you talked about. Conventional computing is becoming much more efficient, so there are, like, the optimization game is not like the core card that you can play because they're hyper efficient. And where do you see use cases? I mean, quantum sensing has been a big hype. We talk a lot about quantum cryptography, post-quantum safe cryptography. It seems like there is at least a lot of companies that emphasize revenue today with hybrid solutions and push that. And we talked in before this conversation about you saying, well, we only have engineering issues, Anders. Don't worry about middleware and software. That will follow. And you kind of sort of repeated that before. So, but aren't there, like, near term or actual use cases where there is revenue to be made now or in near future?
So let me, going back to this, um, why quantum computing at AWS. So what we do usually start with customers, and this is no different for quantum computing. We have a process which is called working backwards exercise, and it works as follows. You ask a number of questions. The first question for anything that you want to build is, who is the customer? So you want to identify the customer. Then what is the customer problem? What is that you are going to solve? What pain point for the customer you are going to solve by building something specifically? And this happened also for quantum computing. So when we started thinking about what to build in quantum computing at AWS, we did this exercise, talking to a lot of different customers from different industries, startups, large enterprises, governments, national labs, academia, and few things emerged from that exercise. So the very first thing was that customers were frustrated about the lack of understanding around the field. There was a lot of noise, there's still a lot of noise in this space. And customers were asking for a way to determine what is real and what is not. What was real and what was not. I'm talking about 2018, 2019, so it's already a few years. And that's the reason why we launched Amazon Braket, which is our quantum computing cloud service. So as you know, Amazon Braket offers customers a variety of quantum computers built with different technologies and developer tools. Why? Because in this way, customers can observe the trajectory of this technology and make informed decisions, right? About investment, about engagement. So some customers decide to invest in some startups, some customers decide to hire talent and build a team to look into quantum computing. And this is the reason why we decided to launch a cloud service, really to help customers understanding what is happening out there. On the other side, we also decided to embark ourselves in building superconducting quantum computers, and this is a long-term project. And we felt that there was an opportunity. We felt that the scientists in the team were proposing an approach which is differentiated, is different, it's compelling, and on the basis of how we see people using high performance compute resources, definitely quantum computers will have an impact. Think about the use of the Department of Energy supercomputers. So if you think about the DOE, Department of Energy Insight Awards. So this is a an award that is out there every year for people that want to use node hours of uh, supercomputers of the Department of Energy. There is a good portion of the use of these machines when it comes to the Indset award, specifically allocated for simulating physics itself. And in fact, if I'm not mistaken, about um, between 30 and 40% of the node hours um, allocated for the in the context of this award is used for simulating physics. Think about high energy, think about fusion, um, quantum chemistry, and other areas that at some point will have um, will be related to quantum computing itself, like simulating molecules and materials, for example. I think that about in 2023, as part of this award, about 5 million node hours of the DOE supercomputers, which is 8% of total, was used specifically for simulating molecules and materials. So you see that these are areas where quantum computers are going to have an impact for sure. And so it means that there is a clear reason to build quantum computers, because once you have quantum computers, you could think that a good portion of the use of these supercomputers will be augmented or replaced by quantum computers. And I don't think that in a way quantum computers will make traditional high performance compute, traditional HPC obsolete. They will augment it in some way because they will allow us to explore new regimes,
What do you mean
and
by
they will.
augment? You mean basically to outsource capacity, so you do a part of the process. If you look at like the material uh, um, sciences, you look at like doing parts of it on an HPC on a conventional computer, and you outsource some part to quantum
with
computing,
good
or what do you
with
mean?
good probability. Yeah.
Okay.
Take some chemical reaction analysis of chemical reactions, battery materials, let's say, or uh, problems related to, one problem that people mention pretty often because people have done a good resource estimate is nitrogen fixation catalysis, which is something needed for fertilizer production, right? So something high impact. Maybe that's where a quantum computer will have a role. Maybe the so supercomputers struggle, of course, to solve these kind of problems. That's where there will be some new HPC pipelines that will solve in part the problems with traditional technology, or the new technology that will be proposed in the future, of course, HPC, but for a specific computational bottleneck, that's where the quantum computer will have a role. So for a specific computational bottleneck, you can use the term outsource, right?
Yeah, yeah, yeah.
And then you can outsource the problem to a quantum computer. And I think it's important already to do some resource analysis on this kind of high value problems, because we will have a better understanding of the timeline as well, right? So people keep asking when are we going to have a quantum computer? A quantum computer for what exactly, right? Because
Yeah,
this
yeah.
is not going to be something like it's not like going to the moon. Either you go to the moon or you don't go to the moon, right? Let's define what it means to go to the moon.
Yeah.
I go to the moon if I can put a foot on the moon, and then I can go back home safely, right? Let's use this definition here. When people say, oh, when are we going to have a quantum computer? Well, the question is a fragment of a larger question, which is what are we going to have a quantum computer for solving problem X, um, independently maybe of how feasible is this problem today, right? But going back to the raison d'être, the reason um, of doing quantum computing in the context of a company like AWS, there are these two directions for us specifically. There's short term and long term. Short term, Amazon bracket, So engaging with customers today, offering a service that customers can use to understand what is the state of the art of technology and decide to engage or to invest. And second, long term, we have an opportunity. We believe we are differentiated. We managed to hire very good talent in this space, and we want to see the bottom of the story. And Amazon invest in some long-term bets. Think about Kuiper. I think we were talking about Kuiper last time we spoke, right? So Kuiper is this project that aims to build over 2,000 satellites for the global internet. Consider out there is probably half billion people that today they can't access to the internet. Kuiper is an opportunity to solve this problem. It's going to be very, very impactful. How long it's going to take before it's deployed? It's going to take years, right? And a large capital investment. So quantum computers should be interpreted in a similar way. But if you look deep in the future, then you can see the reasons why it's important to do it.
Hmm. Yeah, but I mean, I was also referring a little bit to the like the aspect of, like if you look at security. I don't know if you think about this, or it's within the scope, but you know how you have the whole harvest now, decrypt later type of thing. So isn't there, like, with now having algorithms or having, patents in play for safe quantum cryptography, isn't it there's a huge business opportunity also right now for migrating or like forking some new quantum environment to have a quantum ready environment? Isn't that kind of sort of solutions that could be sold or applied right now?
So, as you know, quantum computers in the fullness of time are going to be a threat to certain type of cryptography, specifically RSA and elliptic curve cryptography. They're going to be both insecure against quantum attacks, but there is a lot of activity out there happening in this space. There are organizations that are proposing new protocols that are conjectured to be resistant against quantum attacks. Now, even us as AWS, we contribute as a number of other organizations to verifying, to studying these protocols. And we need to listen to what NIST in the United
Yeah.
States, or ETSI, they are proposing.
Hmm.
Audit infrastructure to see where the uh, criticalities can be, where the vulnerabilities, that's the right
Yeah.
term, can be. See what the blast radius could be associated to some specific attack, and start understanding what needs to be done to move towards post-quantum cryptography,
Yep.
replace the protocols that are known to be weak against quantum attack. Sometimes is the option of that some companies are actually following, of defense in depth, meaning keep using current crypto system, adding another layer. But you see, all of these is happening out there,
Hmm.
and should happen. It's natural. Now, if you ask, oh, how long is going to take before I don't know, let's say um, a quantum computer is going to break RSA 2048, and so it's still in the realm of science fiction, breaking RSA 2048. But I think that quantum computers, to some extent, have been even interesting when it comes to stimulate a novel conversation, a novel discussion in cryptography and in mathematics, because
Hmm.
given the existence of Shor's algorithm, people did a lot of interesting mathematics
Hmm.
around
Yeah.
cryptanalysis, which is interesting, right? And
But they're coincidences. They happen. It's not like there is a master plan behind it, then, isn't it? I mean,
that's right.
my view of it, isn't it? So that's why
Absolutely.
it's important. That's why important. We push for progress, and then we discover a new realm, and we stumble upon progress. That's how I
Yeah,
see it. Yeah.
absolutely, absolutely. Yeah, and it's very interesting, right? That these discoveries have fueled
Mm.
novel mathematics, for example, novel ideas in information security. And I want to hope, and I'm very confident of that, that some of these ideas will turn out to be useful somewhere else.
Mm.
And and this makes me think about a an image that I kind of like, which is quantum computing analogy with other phases of discovery, like the space program,
Yeah.
Kennedy space program. The idea
Okay.
was to go to the moon, and to go to the moon, we ended up to invent a lot of interesting stuff,
Mm.
like fireman suits,
Yeah.
right, or LED bulbs. And this is going to happen also with quantum computers, and is already
Yeah.
happening with quantum computers. Think about innovation in cryogenics, innovation in wiring, better understanding of materials, better understanding
Mm.
of quantum physics itself, which is a different story. But the stuff that people had to come up with in the lab in many different areas, from superconducting devices, neutral atoms, light. Think
Right.
about the single photon sources
Yeah.
have been developed especially in the context of quantum computing, right? And all of these innovation happens because of the flywheel
Mm.
created by quantum computing itself.
Mm.
Not saying that quantum computing is an excuse for innovating across the board, but it's an opportunity for sure. And cryptography is part of this as well. Think about
Mm.
the new stuff that have been studied in mathematics, like shortest vector problems, for example, on the basis of the existence of Shor's algorithm.
I mean, that's my critic point, not being a physicist. They come at it and I said, I'm not the one that keep inventing all this stuff. And I'm not the one, I'm just observing how progress happens. You could even look at wars. It was a terrible happenstance where all the great minds in quantum physics got drawn into this terrible creation, but it sparked a huge progress in science and technology in the aftermath. And pouring the money, putting the brightest minds. That's why I've been very outspoken about the fact that it seems that another Nobel lecturers in the future will come out of a corporate environment where you could do the same. You don't apply like the hierarchical structures of academia. You don't have to have the funding up front because you work in that environment, and also the publishing part, and kind of sort of quote unquote justifying the academic credibility world. You could actually work on the open heart in the business world. And I don't have the outline of which problems will be tackled, but it seems like we have an infinite capability of discovering new things, be it as a result of working on a different problem. But if you put money and the brightest minds into working on actual problems, you happen to discover some great things. And that's more of a romanticizing on the capability of human beings, maybe, but it's something that I've been looking at over the years. And it's very, to me, it's very nice to hear you talk in the same direction, right? That there are some coincidences and we make progress. But I wanted to just like get a little bit into the second part that you talked about, building the quantum computer at AWS, and also the progress in the field. There's been a lot of communication. The big players are now hyping or communicating, whatever you want to choose as a term. We had Willow with Google. We had the big Majorana one chip communication issue that was hyped and then corrected. We had Jensen Huang coming out saying quantum computers are decades away, then having a very hard focus on quantum. Where do you see the field evolving throughout this year? And the second part of the question would be, because as I look at it as an outsider in the field, I kind of saw Ocelot sneaking in the back door. So maybe you could talk a little bit about how you guys, with your approach, seem to have made a huge progress, almost a little bit more silent than the other communications that we saw over the past month. So maybe you could just give me like your reflection on the industry and the other players and the competitiveness in the market.
Sure. So innovation is happening in the industry. There is a number of different approaches to build quantum computers. Now, if you ask me what's the best approach, I wish that I had an answer for this. I don't know. What I can definitely tell you is that there is more knowledge today about superconducting devices than some other modalities. Why? Simply because they have been studied for longer, and there is more people that have studied superconducting devices. There are large corporations that are using this approach. There's a number of startups that were funded with spectacular scientific teams, very strong expertise that are innovating in this space. So it looks like that superconducting devices are a good candidate to scale. And I use this term scale because if we want to solve important problems, we will need to have many qubits of good quality. So good architectures that allow us to scale, but also error correction. As you know, so all the community is moving from the NISQ phase to another phase where people look at proof of concept, look at demonstrations of error correction. And I think that this is very interesting. So NISQ stands for noise intermediate scale quantum, right? For the people that are not familiar with this acronym. So a NISQ machine is a machine that does not try to correct errors. And for a while, people have tried to do experiments with such machines to see if they could solve some important problem. Of course, term important here need to be used in the right way, because what does mean for a problem to be important? Yeah. But so it looks like, at least for commercially relevant problems, let me use this expression, NISQ has not been so far successful. But this is not the end of the story. Maybe people will come up with a single purpose machine, or a machine that is not necessarily a universal quantum computer, meaning a computer that could solve any problem, just specific type of problems. And maybe there is an opportunity there, but we don't know, right?
Can you
And
elaborate
still,
a little bit on the error correction and the noise? If you say that maybe there is a computer, do you think there will be less noise, or do you think it will be better on error correction? What is the, when you say they could, because I see the NISQ state as an intermediate state towards stabilizing a larger quantum computer. But if you say there you think you can be approaches, what would they be in your view?
so during the NISQ phase, people have studied quite a bit these algorithms that use a quantum part and a classical part back and forth, variational algorithms. And on paper, there are some results that tell us that variational algorithms could, for certain problems, have some interesting uses, but experimentally this has not been verified. So it could be that NISQ is not over yet. There were a lot of expectations about NISQ, and it looks like that people are now moving towards this idea of error correction, demonstration, and proof of concept. So at AWS, our hardware team has been very convincing in telling our leadership and telling me as well that error correction is fundamental. And they wanted to start building quantum computers keeping error correction in mind from day one.
Mm-hmm.
And in fact, Ocelot that you mentioned
Yeah.
is a device that demonstrates error correction in a scalable architecture. Scalable architecture means that you could almost interpret this machine as a module of something that can be built in a way that could scale.
Mm-hmm.
And scalability, it's a crucial term because you could today build a quantum computer, let's say with X qubits, where X is sufficiently large to tackle some problem that is very hard to simulate with a traditional computer, and maybe impossible to simulate with a traditional computer. The issue is what is next.
Mm-hmm.
Once you build that device, how does this device teach you what to do next?
Mm-hmm.
And having a machine that is in the NISQ regime, and already there are such machines, because once you have, let's say, 80 qubits and a few thousand gates, then you already are in a in a territory that it's very very hard to simulate
Mm-hmm.
with classical computers, right? But even if you are stepping inside that territory, does this help you to scale and have a better quantum computer? Well, not necessarily. Maybe it's just a dead end. And I think that the value of an experiment, and let me use this term like Ocelot, I don't use term device, let me use term experiment, just to give you the feeling that this is a single step out of 100 steps, right? So the value of an experiment of this type is that it teaches us a direction, a new way for potentially scaling.
Mm-hmm.
And as I was mentioning, our hardware team has been very convincing about the importance of error correction from day one. And I agree. So I think that error correction is super important. And in order to build a quantum computer that is going to be truly impactful, we need to burn down risks. And learning about error correction is fundamental to get there.
Can you talk a little bit about how cat qubits are different and how that applies? Just
So usually I like to
because it's
so my knowledge of this field is limited,
okay.
and I like to have the experts talking about this subject. I I like to see error correction with respect to the systems in the following way. A qubit can be represented as a point on a sphere. If you think about qubits in the in fact, if you think about bits, you can build a bit out of a lot of different things out there, right? Any object that can be set in two states, which are uh, different and observable, can be seen as a bit, right? Like I take this pencil, right? So vertical means 1, horizontal means 0, and by doing this, I'm performing computation, right? So this is quite boring computation, but if I have maybe a million of these next to each other, I can do interesting stuff. For a qubit is different because a qubit cannot be represented with a pencil, but it's a point on a sphere, and you have the north of the sphere, which is, let's say, 1, the south is 0, so the antipodes. And mathematically, it's beautiful that since you have a point on a sphere, it's a combination, which technically is called superposition of 1 and 0, right? But then when you observe with respect to specific type of observation, then you get either 1 or 0 with certain probability, depending on where you are on the sphere. So when you think about cat qubits, it's really about taking the sphere and stretching it so that the one gets farther away from zero. And so in quantum computing, there are two types of errors, right? If you think about traditional computers, my bit 1 could be flipped at some point with a certain probability to 0, and 0 could be flipped to 1, and I can't control this. This is an error, right? So I can build some redundance and in this way try to correct the error. Like the simplest thing to do would be take two pencils, right? And I set them to 0. Well, now two pencils is not really great because if some of them flips, then if the other one doesn't flip, then I don't know what to do. But if I have three pencils, right, or four pencils or five pencils, then if one or two start flipping, then I can take a majority vote. I can see uh, which of these pencils are in a different configuration, and I can try to reconstruct what was the original state, right? The state before error occurred. Now, I cannot really do this in quantum physics, right? Because there is this thing called no cloning theorem. So I cannot take a qubit and make many copies of these unknown qubits and then just go there and measure. I need to do something else. I need to encode information in a very complicated way, which is beautiful, by the way, because it opens up a whole new direction in mathematics, right? So going back to cat qubits, think about that there are these two errors here, not just bit flip, but there is bit flip and phase flip. So bit flip is 1 becoming 0, 0 becoming 1, and phase flip, you're on the sphere, you can move around. So every point on a sphere can end up on every other point, and you can decompose this error into two errors, two type of errors. So, well, the bit flip is natively corrected when you use cat qubits because you take the sphere and you stretch it somehow, the one gets very far from the 0. So this is my way to visualize it. Now, if this is the best way, if this is the most correct way, I don't know, and apologies uh, to the experts that maybe don't like this. But then what you do, once you natively correct the bit flip, then you need to correct the phase flip, and but then you can actually make let's say copies. You can have multiple of these spheres stretched, and you can try to correct the phase flip. So to cut it short, cat qubits provide a technique for natively correct one of the two errors that naturally occur in quantum computation, and that is necessary to be corrected in order to be able to perform useful computation. Now, is this the best approach? I don't know.
Well,
So I don't know.
what, how would you compare it? I mean, how do you see the race for commercialization? Who are players? Do you see it happening among the big seven? Do you see it happening on some startup level? I mean, you've been involved with some of these players before. Which companies would you bet on? I mean, where do you see the approaches? There are, I don't know, seven, eight, nine different quantum computing approaches that have their own expectation to be promising. Where do you
Yeah.
see it?
So let me try to answer this in two different ways, in two phases. So
Mhm.
first, we have a service, Amazon Bracket.
Mhm.
We provide access to different type of computers, and I need to be as open-minded as possible. Meaning that if at some point there is a startup out there that comes up with a very interesting idea, and customers want this hardware, this new type of hardware on the service, then it's my job to provide access so that customers can use it, right? And and I can tell you that I've been talking to every single company that is building a quantum computer out there
Mhm.
during the last 6-7 years, right?
Mhm.
And it's exciting because there are certain innovations that maybe are happening in areas that are not so developed. I mentioned superconducting devices. There is more work done there, but there
Mhm.
are some other emerging fields and surprises. There can be surprises. There's neutral atoms. They are scaling. There's a number of startups that are building uh, very interesting, that are performing very interesting experiments with neutral atoms. There are ion traps that have also been studied for many years and are more understood. There is light, clearly. Of course, each of these modalities have their plus and minuses. Some people say, well, superconducting devices are going to be very hard to build because every time to build a chip is like a snowflake. The level of precision that you require to build them is so high that there is no way you can scale them because at some point they're going to be too complex, right? So this is a criticism that some people move towards superconducting devices. Then there is the criticism that some people move towards neutral atoms or ion traps, saying, oh, the clock speed is too slow, you won't be able to implement error correction. But again, we need to be open-minded. And there are some emerging areas as well, like silicon qubits. These are areas that somehow are less studied. And specifically because they're less studied, it could be that are reserving for us some interesting surprises. And so uh, we need to follow what is happening there and be optimistic about innovation. Then, in the fullness of time, there's going to be a winning technology. Maybe something will emerge naturally because of a specific discovery, maybe on the engineering side, that will show us the way. But there is also the possibility that a number of these technologies will keep evolving in parallel, and we will end up to have maybe quantum computers for different purposes. I mean, the story of quantum computer for different purposes is a little bit strange, right? Because it's a bit early to talk about this, I think. But maybe there will be some applications associated with generating data that come from quantum systems. And if people will find out that some of these data are useful, maybe they will build a kind of device that is not truly a quantum computer as we would intend. It is a machine for manipulating matter in specific ways and generate data. Maybe this data can be fed to some machine learning system for gaining information on some process that is valuable to know. So to cut it short, let's stay open-minded and keep an eye on what is happening out there and try to support all the modalities.
I like that. I mean, you're building your own, but you're also like agnostic on running the services on the computation and having the environment of the services that you provide. I like your approach to supporting the industries, and I think this is what it's all about. There are many unsolved questions. Do you? I want to round off with circling back to where we started, but where do you see the engineering biggest hurdles right now? What are things that you think are like points that could be overcome in near midterm future that would kind of sort of speed up the number of qubits, or to make some rapid progress, or some announcement that could fuel the industry with investments? Or do you see like there are some pivotal points, some, I mean, engineering barriers, if you like, that we need to overcome?
So I think that the fact the whole community is shifting towards error correction is already a good thing, and it's already meaningful. It shows that the question that have been historically asked, how many qubits, becomes somehow, and I don't want to say paradoxically, but somehow less important, because it's really about the quality of qubits and the possibility to scale. Of course, we will need many qubits and good quality qubits, right? But the fact that the industry is shifting towards experiments that are looking at error correction is already meaningful, and it's a good sign. I think that this is a signal for investors, and it teaches investors that error correction is really, really important, and hints to the fact that you as an investor want to have a foot in quantum computing, then you should start asking questions around error correction rather uh, rather than, oh, how many qubits do you have, and how many qubits can you build next year or in a couple of years. I think that this is a shift that brings the game to a different level and brings depth to the conversation between investors and hardware builders.
If I could have a follow-up question on that, do you think, I mean, if we assume there will be a more rapid progress on the capabilities and breakthroughs, if we would extend the periodic table with new elements through the material sciences, and we would cure all these diseases, and we tackle climate and all the the visions that might be out there. Do you think our economy is ready for such powerful technologies? Do you think we need to change how capitalism, how the economy is? Because I would imagine if there is a quantum supremacy, if there is a breakthrough, if there is a race towards the commercialization, it's so powerful in many fields that we will have new, maybe $1 trillion industries. And are we, as a society at large, is the economy equipped for this type of breakthroughs? If you look at the intersection of quantum computing and AI and exponential technologies. I mean, I don't know if this is a topic that you thought about, but I would be curious about your opinion.
So I think that if you think about the applications of quantum computers with good probability, the very first applications that are meaningful, maybe from an economic standpoint, are still going to be associated with science, right? Now, what is the value that you can give to a dynamic at simulation on spin system, right? This could be the very first applications, or something like simulating a physics model. For the people that are familiar with this terminology, Fermi-Hubbard ground state simulation, let's say. It's very hard to determine what is the economic value of these discoveries. I'll use this term. And if quantum computers are going to impact science before anything else, can we associate a monetary value to what quantum computers will allow us to learn about our universe? Almost like how much is the monetary value of, now I'm going to say something which is a little bit bigger, I don't know, relativity theory. Can we associate a number to that? Maybe, yeah. I mean, GPS today are able to function because we can do certain computations on the basis of our understanding of relativity theory, right? Now, quantum physics itself, and I want to try to answer your question in the broadest possible way. And so think about quantum physics. NMR machines. We can build NMR machines that are obviously very important in the biomedical context on the basis of our understanding of quantum physics. Lasers. We can build lasers on the basis of our understanding of the theory of light, which is again quantum physics. And transistors, clearly. Transistors are part of our computers today. What is the monetary value associated with the understanding of quantum physics at the basis of what is needed to build transistors? It's very hard to pinpoint, right? And even in terms of timeline, it's a long stretch timeline of half a century at least. There is a chance that quantum computers will unlock scientific discovery associated with quantum physics in a similar way. And maybe one day we are going to build some device that is not going to be called quantum computer, maybe it's going to be called something else, but we will be able to build it because quantum computers allow us to discover certain ideas, certain facts about our physical world that then can be reused for that device.
Mm.
So I think that this will happen organically through an amount of time that will be long enough, maybe not to see a disruption of the economy happening overnight. This is not about moving the stock market. You see what I mean?
No.
Like, this is something really about. We are still trying to understand what are the consequences of the discovery of the atom, right? Today,
Mm.
if you think about it.
Yeah.
So we are still discussing about the value of nuclear energy, whether we should use nuclear energy or not, what is the best way to build it, what is the economic impact,
Yeah.
and we have been and we have known nuclear energy at this point since a while, right?
What is the most exciting thing that you're looking into like this year for AWS for your sections in quantum?
So I'd love to see customers um, coming up with important feedback
Mm.
to the people that are building hardware. I would like to see people understanding a bit more, as I was mentioning before, that the timeline for this field is going to be uh, quite long, right?
Mm-hmm.
And so, um, seeing the right, I like to see people having the right expectations. Really culturally, I'm not sure if this answer satisfies you, but so to me, it's very important that investors understand that this is a long-term bet for everyone, and that really requires sustained investment, continuous funding for research, for development, for infrastructure. So I like to see interesting collaborations happening. I think that progress really depend on strong partnerships.
Mm.
I mean, strong partnerships that include academia, industry, governments, knowledge sharing. So I like to see these. I also would like to see, and possibly my list of wishes here is going to be probably too long, but um, you see, when it comes to the global supply chain, right? Sometimes people forget the complexity of the supply chain for also for building quantum computers. This requires specialized materials, components, and even expertise, right? That span multiple disciplines and geographies. So I hope that at the policy level, people will have a clear understanding that um, that boundaries in quantum computing may not be so that, or rather than using a negation, that boundaries in quantum computing may be a problem, right? So I'd like to see also from the point of view of so when it comes to talent, when it comes to education, I like to see people choosing, so the next generation of scientists and engineers to choose the right areas,
Mm.
to focus on the right areas. And there's lots of interesting things happening in quantum computing. Um, and some of these areas are still completely uh, completely new. Like the interplay between machine learning, for example, and quantum computing, it's extremely interesting, and somehow traditionally has been more about if you have a quantum computer, how can a quantum computer impact machine learning in terms of the complexity of algorithms? But there may be other opportunities. As I was mentioning, maybe once you have access to quantum data, you can use this data to do something interesting with classical machine learning. And I'd like people to see a bit deeper that direction.
Yeah.
And yeah, so and now if you ask me what could be impactful in 2025, again, systematically reducing logical error rates to bring us closer to the level needed for useful quantum application. This is what everybody would
Everything.
wants to see, right? So having new demonstration of logical gates, let's say between multiple logical qubits, it's important. So anything that brings us closer to fault-tolerant quantum computers is it's valuable.
So we're just looking for the surprises then, I guess. It's just hard work and moving on, and then there'll be some surprises along the way,
Look,
hopefully.
there are lots of technical challenges that still need to overcome. I think that one of the people that use this metaphor of the marathon, not a sprint, is Chris Monroe, one of the
Yeah.
founders of IonQ. Quantum computing is a marathon, is not a sprint. Sure, where are we today? Uh, Marathon is 42 kilometers, right? So we are still early kilometers of this marathon, and uh, again, there are significant technical challenges that still need to be overcome. But I think that the whole industry, hopefully, by giving attention to error correction, is going in the right direction.
That's a good way. And let's end it with a very simple question. Do you think consciousness is related to quantum physics?
Oh, this is a question for Hartmut Neven.
Yeah,
Um,
of course. It's also for Hartmut Nevin, and we could take in Roger Penrose and the ARC stated. But what is your feeling? I mean, do you think this wet fluffy little thing has something to do with quantum physics? I mean, I don't know if you're familiar with the ARC OR theory from Penrose and Marco-Tubuli and everything, but I just starting on a philosophical note, I just wanted to end on to me the most beautiful thing actually just listening to you and having the experience and learning that something that no computer can take away from me. It feels like it, and just wanted to end off your personal hinge on that.
so I'm not an expert on this subject, so I don't have a solid opinion. Um, I tried to ask this question to Roger Penrose. So Roger Penrose was the advisor of my PhD advisor, and I had an opportunity to meet him at the so in London during the service for Stephen Hawking.
Mhm.
So and I uh, so he was trying to get a cab, so I helped him to get into the cab, and there was a part of me that wanted to ask him question of this type, but then I said, look, maybe every single person that is next to Roger Penrose is going to ask him about consciousness and quantum, so I better help him to get in the cab, and I'm going to be I'm going to be
I would
useful
have
at least.
asked. I would have asked. Yeah.
So um, I think that there will be definitely interesting surprises coming out from quantum computers, right? Building quantum computers is again a scientific opportunity, and it could be that once we will have quantum computers at scale, we will be able to perform experiments that will allow us to also have a deeper understanding of what is happening in our brain. So why we should exclude this, right? And it's hard to predict what people will do with quantum computers, but once you have a new instrument for peeking into physical reality with the level of precision and with the level of depth that quantum computers will allow us to have, then I'm very confident that people will figure out new ways to new ways to use them and potentially to try to approach some of the questions associated also with the function of human brain.
Thank you, Simone. Picking into the reality by quantum computing. It's wonderful. Thank you so much for sharing the time this morning with me. I've picked up and learned a lot. Appreciate it. And
Thank you.
yeah, thank you for taking so much time, and hope to meet you in physical
Absolutely.
reality at a
Me
later
too.
point to have some discussions.